Hello, thank you very much for having me as a speaker. I'm looking forward to this. Today, the talk is going to be about hardware security from the hacker's perspective. So we'll cover attack surfaces, techniques, and why any of it matters. By way of introduction, I am Ethan Shackleford. As was said, I'm a security consultant at IO Active. I've been there for 2 years. My focus is on embedded and hardware security primarily. And what do I mean by hardware security? So hardware security is a very broad topic. Attacks can range from $5 in 5 minutes to tens of millions of dollars and years of research in the case of something like smart card security research. This talk is going to focus on the low to medium effort attacks, as those are the most common attacks and also the most accessible. So why does any of this matter? In the era of the cloud and software as a service, why should anyone care about hardware? Well, as the saying goes, there is no cloud, just other people's computers. That hardware didn't disappear, it just moved somewhere else. This is also true because of IoT. This is a very quickly growing industry, becoming more and more important in our lives and work, building automation, smart everything, security systems. All of these things need to be considered from a hardware perspective before they can be considered secure. It's also important to remember that the I in IoT stands for internet. While it may not sound particularly threatening to have your smart bulb hacked, that is connected to your network, and it could mean compromise of everything else on your network as well. Same, of course, goes for network infrastructure, so routers, modems, range extenders. This is even more true because of telecommuting. I'm saying this to you over Zoom, so applies more than ever. And of course, the automotive and industrial control system industries, like every other industry, continues working along with hardware. So I want to begin the talk with a story, sort of a cautionary tale about Nintendo. When the original Nintendo Entertainment System was released, Nintendo wanted a way to control the market. They didn't want pirated games or unlicensed games to be playable on their system. In order to do this, they designed a lockout chip known as the 10NES chip. So the software running on the chip was effective at preventing piracy on unlicensed games. A great deal of money and effort was spent by Nintendo to make sure that this was the case. And they did succeed until as recently as a few years ago. The exact authentication mechanism that the lockout chip used wasn't fully understood and wasn't broken in software. However, almost immediately, a trivial bypass was discovered for the lockout mechanism pretty quickly after the release. So just to talk a little bit about how the 10NES chip works. There's a lock chip, which is inside the NES console, and a key chip, which lives on licensed game cartridges. When a cartridge was inserted, the key chip would communicate somehow to the lock chip in the console and would conduct some kind of authentication handshake. If this authentication handshake failed, the lockout chip would proceed to reset the NES and try authentication again and rinse and repeat, effectively preventing the NES from doing anything until either the cartridge, the unlicensed cartridge, was removed or, But what Nintendo failed to consider, and what the 1980s hardware hackers very quickly thought to consider, was what happens if the key chip never tells the lock chip that it's there. The answer to that question is nothing. The lock chip doesn't do anything because it doesn't realize a cartridge has been inserted. It never gets to the point where it begins to reset the NES. And just like that, some kids in their garage with wire cutters have defeated probably millions of dollars of investment and time by Nintendo to prevent these unlicensed games and pirated games from being played. So the moral of the story here is it does not matter how good your software is, because it's only as good as the hardware that it's running on. So as a hardware security researcher, as a hardware hacker, there is a useful analogy to networking security when presented with an unknown device. When you're working on a network target, one of the first things that you're going to do is run a network scan. You want to determine what ports are open, what services are available, so that you can make a judgment on where there might be some exploitable service or vulnerable process. The same is true of hardware. the question you want to ask is, how does this device communicate with the outside world? There are a ton of ways this can be done, but there are a few very common ways, namely Ethernet is very common, USB, wireless, of course, especially with IoT, Wi-Fi, Bluetooth. These are all relatively common to see. And once you've enumerated what this external attack surface is, you can leverage any number of these interfaces potentially to gain further access to the system. The next step at when I'm presented with an unknown device in understanding it is to analyze the internals. Most production devices nowadays are not a single chip. It's many integrated circuits and passive components all communicating and working together to operate whatever the device's task is. Pictured on the left, you see a semi-close-up shot of an old wireless router. The big chip in the center marked Broadcom is the CPU. Underneath, the two narrow chips, those are RAM. And on the right, with the chip marked Intel, is a flash memory device. This is analogous to a hard drive on a laptop. So these chips need some way to communicate with each other. And if you see in the picture all of these dark green lines running between the various components, these are traces, and all they are is copper wires. And these allow chips to communicate. There are tons of different ways that this communication takes place, different protocols. But an important detail about most of these protocols is that they're not protected or secured in the same way that, say, HTTP is with TLS. So they can be an important avenue for either information gathering by sniffing the lines or exploitation by injecting data onto the lines for an attacker looking to access hardware. A very good example of this is SPI flash memory. So as I said before, flash memory is a very common form of long-term storage for embedded devices. SPI, or serial peripheral interface, is a common protocol that integrated circuits might use to communicate, especially common for flash storage. So pictured to the right is another wireless router, a slightly newer one. In the center is the CPU. To the left is the RAM, which we'll ignore for now. And to the right, in the top right of that smaller chip, is the flash storage. So for this particular wireless router, it's running an embedded Linux system. And so that flash storage is going to contain the Linux kernel, it's going to contain the bootloader and the root file system for this device. The SPI chip, the CPU communicates with the flash chip over a serial peripheral interface. And just like the CPU can communicate with it, we can as well. Oh, and to note, obviously within the root file system of the device, system binaries and libraries, configuration files, and files like etc shadow and etc password that can very easily be leveraged into further access to this device. So in order to extract information from the SPI flash or dump the firmware, there are a ton of tools available. There are dedicated SPI read, write tools. Those are generally cheaper. There are also tools like what are pictured here in the red device in the corner. This is called the Bus Pirate. This is a device that you can connect to your computer over USB, and it will communicate in SPI to whatever you hook it up to. It also speaks a few other protocols. These are about $40. They're a handy tool if you do lots of different sort of hardware testing. Now you may look at this picture and wonder, how did I know what to hook up to? How did I know what the pins were? Which brings us to a really important topic in hardware research and embedded security, and that's something called a data sheet. A data sheet is a piece of documentation that contains all the information you ever would need to know about a given integrated circuit. So in the case of the SPI chip, it's going to contain how much storage space it has, what each of those pins do, exactly what commands it supports, like how to read and write from it. So by dumping the firmware, it can be extracted and analyzed and to determine if any vulnerabilities exist in that firmware that we can use from the outside to exploit the running system. Additionally, if no secure boot mechanism or encryption is in place on the storage, it can also be modified and written back to the flash to, for example, have it spawn a root shell as soon as it starts up. I have an example here, a demonstration of exactly what was just pictured in the last slide, dumping firmware from flash memory. So the first line here, I'm using a tool called FlashROM, which is designed to do exactly this, extract data from flash memory. I'm telling it that I'm using a bus pirate to interface with flash and that I would like it to save the information that it extracts to flash.bin. Now, dumping a raw image from flash memory, or from a hard drive for that matter, doesn't produce a neat file system image that you can just mount most of the time, or clear data structures. It's generally just one big long blob of data. So tools exist, for example, binwalk, which is used here, that can analyze this data and extract meaningful chunks, meaningful structures out of it. So the output of this goes on for quite a while, doing lots of extractions, but part of the extraction is the SquashFS file system. SquashFS is like NTFS for Windows. This is just a file system format, and it's designed for flash devices, SPY Flash, and similar devices. And so we can see here at the top, just under the ls, this is in fact a Linux root file system. We have bin, dev, etc, user, etc. And interestingly, I mentioned that this was a wireless router. Note the web directory there. The main way that you interface as an end user with this wireless router is through a web application. So now that we've dumped this firmware, we can go and analyze the source files for that web application that we wouldn't have otherwise had access to, and potentially find a vulnerability that we can leverage in the web application to exploit it that way. Also, being a Linux file system, there is a password file, in this case, etc password.back. And you can see on the 4th through 6th lines there, we have an admin user with a password hash present. So we can use a tool like John the Ripper, which is designed exactly for this, for cracking password hashes, to attempt to crack this password so that maybe we can use this to authenticate the device and gain further access. Highlighted in red here at the bottom, we see that John the Ripper has cracked the password for the admin user. And you may be suspicious that the time it took apparently was 0 seconds. If you're familiar with password cracking, you will know that this is way, way too short for any good password. And the reason that it is so short, the reason it was cracked so quickly, is a symptom of sort of a wider thing that you'll see in hardware and embedded security, and that's terrible, terrible password policies. So the password that was cracked for this admin user on this wireless router is 1234. We're going to put that in our pocket and write it down in our notes and potentially use that further down the line or in another area to attempt to compromise the device. So the next thing after internal communications and flash memory that the hardware hacker is going to look for on a piece of equipment are debugging interfaces. Most devices will have some kind of debugging interface. The manufacturer needs to program it. They might need service people to repair it in the field. There are lots of forms that this can take. USB is fairly common. For example, if you're familiar with Android Debug Bridge for Android, that's a debugging interface. And there are also these two other interfaces. The first is called UART. I'll go over in more detail in a second what that actually is, but this commonly exposes a console or login prompt or log output, debug output for the program. And they're usually not exposed internally. These are usually internal to the circuit board. The second, which we'll go over a little bit later, is JTAG. This is a hardware level debugging interface. And this is usually going to be vendor, chip family, or model specific. This is going to vary between chips. So looking at these pictures, and if you've looked at circuit boards before, it can be overwhelming. There's a lot going on, tons of components, lots of traces. But if you know what to look for, it can actually be very easy to identify these debugging interfaces when they are present. They usually will share a common footprint, like any given UART interface looks similar to any other given UART interface. And in some cases, the designer will helpfully label them for you, or original connectors may be still attached that you can use to find information about the interface. So in the case of UART, what you're looking for in a device is 4 or 5 pins in a straight line, like you see on the right, circled in red. This, again, is that wireless router we've been looking at. Also, like I mentioned, you might have a helpful designer label them for you. On the picture on the left, inside the red highlighting, you see 4 pins, 3v3, ground, RX, and TX. If you see pins in a row and 2 of them are labeled RX and TX, you have almost certainly found a UART header. So I want to briefly talk about just the basics of how UART communication actually works once you've connected a wire to it. So it stands for Universal Asynchronous Receiver Transmitter. Translated into layman's terms, this basically means that it does not use a clock signal and that it just uses 1 data line instead of 8 or 16. The line coding, so the way that 1 or a 0 is sent over the wire, is also very simple. If the receiver sees a line driven low to 0 volts, it should interpret a 1. If the receiver sees a line driven high to, for example, 3.3 volts, it should interpret that as a 0. This results in a pretty easy to spot pattern. And you see in the diagram on the left here, this is a square wave pattern just going up and down between 2 levels. So that brings me to my next point. Oftentimes, you won't get an easily identifiable header. There won't be pins in a row, or they won't be labeled. And you might have to do some digging to find one of these interfaces. The board on the right side of the screen is a good example of that. There are no obvious UART headers on this device, and there are lots of test pads spread all over the place, and none of them are labeled. So how would you figure this out? Well, you can use an oscilloscope, which, if you're not familiar, just measures voltage over time. If you remember from the last slide, UART communicates by changing voltage over time. So by probing the board and probing various test points and looking at the output, you can look around and wait until you find something that looks like a square wave. If you look at the top half of the left section of the screen on the oscilloscope, we can see that same pattern we saw on the chart before, up and down two different levels in a square formation. And so that can help you identify these interfaces. The board on the right is an example of where that technique was successful. Probing was able to identify where on the board these pins actually were, and then they could be attached to, and the UART interface could be communicated with. So how do you actually talk to it? USB to UART adapters are cheap, and they're available everywhere. FTDI is the main vendor who produces the chips that make these work. You can usually find them for $5 to $15. TTL, which stands for transistor to transistor logic, which is basically just the type of communication that are usually found on these interfaces, are between 1.8, 3.3, or 5 volts, depending on the device. You do need to match that level to your target. If you use, say, a 5-volt adapter on a 1.8 volt interface, you'll probably do some damage, or at the very least won't be able to communicate correctly. On that note, also very important, if you're purchasing one of these and want to try this out, to make sure you are buying TTL and not RS-232 or some other similar serial protocol. RS-232, for example, uses negative 13 or 15 volts to positive 13 or 15 volts, which will for sure do some damage to your target. So definitely make sure you're using the right adapter. So who cares? Why is this interesting? UART interfaces are usually intended for logging output, administrative access, and debugging access. In the case of an embedded Linux device, this is often a login prompt or debug output from various applications. And for embedded devices, this might be a command shell or log output. Now, even if there is, even if it's logging only or it's entirely unused by the main application, doesn't make it entirely useless necessarily, because all stages of device operation can make use of the UART. including the bootloader. So even if the main application isn't using it, it's possible that the bootloader is, and you can interact with the bootloader in that way. So I have a video here just demonstrating connecting to the UART interface of the router we've been looking at this whole time. PicoCom is just a tool for interacting with those adapters that we just talked about. So I'm going to play the video and power on the device. And first, we're going to see some information referencing U-boot. This is the bootloader starting up. It's going to do some configuration, and eventually it's going to load the Linux kernel. The Linux kernel is going to start up, do its own initialization, and eventually start the system applications, start whatever it is that this router uses to actually do its work. So near the end of this log output, there's actually an interesting detail, which should pop up in a moment. I may have mentioned earlier that this device exposed an SSH interface. Once we had extracted the spy firmware, we found that password file and we cracked the credentials. And I thought, okay, perfect. I can use these credentials to access this device over SSH. And I tried it and it did not work. It rejected my credentials, authentication failed. This was weird. I didn't know why this happened. I wasn't sure. So I left it alone and moved on. So even if this UART interface does not give us a login prompt, the information that it outputs can be extremely valuable in moving forward with attacks and better understanding the system. You see here the very last line in this output includes dropbear. Dropbear is an SSH server that you usually find on embedded devices. And we see here that this is the command that starts the dropbear server. And at the very end, the very last argument, it's passing this /var/temp/dropbear/dropbear password. Aha. This is probably why authentication was failing. It seems like dropbear maybe has a separate set of credentials. So we can now go back to our flash dump. We can find this file in the file system that we extracted with binlock and figure out exactly what that SSH password was and gain access using that password. So at this point, initialization of the system is just about done. And in a moment, I'm going to press enter, and I'm going to, in order to bring up a login prompt so that I can authenticate with the credentials I cracked and get a shell. So I'm going to play a little bit more logging, hit enter, and turns out I didn't need the credentials at all. This is not uncommon in embedded devices. Sometimes you plug into a UART and you just get a shell for free. You don't have to do anything. And a root shell at that. So yeah, it's a very simple attack. It takes like 10 minutes, but it can be very rewarding. We now have full control of this device. So this is another example where perhaps the actual Linux application doesn't use the UART. It's just quiet. It doesn't talk. But when the device boots up, you can see that U-boot does use it, or the bootloader uses it. A great example of this is U-boot, which is a pretty popular embedded Linux bootloader. And the default behavior of U-boot in a lot of areas is actually kind of insecure. It requires configuration to disable some of this insecurity. So on the left, you see the highlighted hit any key to stop auto boot. What this does is if you are connected over UART to the bootloader and you press a key as it says, it will stop the boot process and it will drop you into a bootloader shell. Now, a bootloader shell, at least in the case of U-boot, is even better than a root shell. It can do all the things that root can do, and it can also reconfigure the Linux kernel. It can read and write memory arbitrarily. It can disable things like SU Linux, which root normally wouldn't be able to do. And on the right, a similar example, even if this hit any key to auto boot thing has been disabled, the default behavior of U-boot on a failure to read from memory is to drop into a shell. So you might see this behavior and be able to leverage that by somehow causing a failure during boot, and then you get a U-boot shell. So moving on, we've covered UART. Now we're going to talk about JTAG. JTAG stands for Joint Test Action Group. It was originally developed for the testing of integrated circuits on more complex circuit boards. When you want to identify a JTAG interface on a device, You want to look for this sort of 2 rows of long pads, either 20 pins, 10 pins sometimes, it depends on the chip. There are a few sort of pseudo standards here. If you don't find something like this, you can also look for labels, just like with UART. TDI, TDO, TMS, TCK, and T-reset are all signals associated with JTAG. So if you see those labels next to pads, you've likely found the JTAG interface. There are also tools such as JTagulator and JTAG-enum that can help you identify or figure out which pin is which. Also want to mention jtagtest.com/pinouts, which contains a helpful reference of some standard connectors. Again, why do we care about this? Why is this interesting? Well, it is ubiquitous. Every modern device is going to be equipped with this kind of interface. Your phone, your laptop, any IoT gadgets. It is also extremely powerful. It's independent of software. It doesn't care about ring level or execution level. It doesn't care about the root user or standard user. And it can read and write memory, debug. It does everything. So here's an example. This is, I have JTAG connected to a microcontroller that has firmware installed on it for locking and unlocking a door. It prompts for a password. You can see the prompt in the bottom right. We're trying a few passwords that don't work, and it's not going to unlock the door for us. At the top left, you can see a tool called OpenOCD. I won't get into detail about it here, but it's just used to communicate with the JTAG interface. And then on the right, we're using the dump image command, specifying flash.bin as our output. And we're getting the first 32 kilobytes of the device, the microcontroller flash memory, which is the whole thing in this case. So we're dumping the firmware. From here, OpenOCD and dumping the firmware. Once we've dumped the firmware, we can use binary analysis tools such as Binary Ninja, IDA Pro to analyze this firmware and see if there's any interesting information we can gather. So either sensitive material, such as this super secret password. This, even without reverse engineering very much, this is extremely suspicious. But we can try this, and lo and behold, when we do, the door will unlock. And even further than this, we can, let's say that this hard-coded password wasn't here, and it's using some very good, very secure cryptographic method for determining if our password is correct. Well, because we have a copy of the firmware, what we can do is we can figure out where exactly it's checking the password, and we can debug. And we can set a breakpoint. If you're familiar with breakpoints and debugging with more higher level interfaces, this is very similar. First, this instruction here, this compare R4 to 0, is checking the return value of the function that checked the password. It returns 0 if the password matches and returns 1 if it does not match. You can see just above, we're manually setting R4 to 0 before this instruction executes. And then when we continue execution, even though we've entered an incorrect password, password 1, we get access granted and the door opens. So what do I want you to take away from this talk? Hopefully an understanding of how a hardware hacker approaches the target, how we think about hardware, and what we're looking for. Hardware security is a super broad field, and quite literally every sector of the tech industry is built on hardware. So this is never going to not be important, and I think it's useful for anyone in the security industry to at least have a cursory understanding of this kind of thing. And most importantly, I hope that you walk away with this from this with maybe a small interest in hardware hacking, maybe a big interest. There is a huge number of super insecure, interesting devices that you can get for like $5, $10. So I encourage you to buy some old routers, get a BeagleBone, get a Raspberry Pi, pick up some of the equipment that I mentioned in this talk, and try some of this yourself. It's easy, it's pretty low risk. You lose a couple of bucks if you destroy a device, but not a big deal. So, and feel free to reach out to me if you have, later on, I mean, I'll take questions in a second, but later on, if you would like some information, I'm happy to help. So thank you.
Thank you very much, Ethan. That was Really, really interesting. I guess one question I have for you is how true is it that, you know, uh, given enough time and physical access, you know, basically it's all over but the waiting, or is it the case that no, they're like you can make hardware that is truly secure?
Um, I think that it, I don't think there's anything that's perfectly secure, but it really depends on
Right.
how much money you're willing to spend. I think that something like the smart card in your debit card, for example, um, so much money and so much time has been put into securing those things, and also a ton of money has been put into trying to hack them, trying to find vulnerabilities, and just this iterative sort of arms race that the security just keeps increasing and increasing to the point that you could do it, but it's going to cost several $1 million in equipment. You need someone who is a specialist with several different kinds of equipment and just lots and lots and lots of time and resources. So I don't think it's possible to make a perfectly secure device, but I think from the perspective of the average user or of maybe an executive who is wanting to increase security, having like a baseline or medium level understanding of hardware security so that they can assess like the stupid attacks, like the root
Right.
shell over USB attacks, is super valuable and
Yeah.
cheap.
Interesting. Any other questions? Everyone should be able to unmute, or you can type it in the chat.
Yeah, I can address some of the questions in chat here. I see Lori asks about common attack vectors to utilize when a secure boot is enabled, and are there different attack vectors between a secure and trusted boot? So to your first question, yes. Usually the attack on secure boot is figuring out how they screwed up implementing secure boot. There are a lot of instances where that's the case, where they just will either incorrectly handle some part of the logic that lets you get like a sneaky incorrect key in there or something, or for example, there are devices which may have secure boot enabled, but they have some kind of boot ROM like device firmware update mode where if you try to just the standard way upload some new firmware, it's going to reject it because of secure boot. But the actual device firmware update mode has vulnerability in itself, so that you can exploit, that then gives you code execution at the most privileged level, and then you can just sort of get around the secure boot thing. I would say it's not so much that there are different techniques for secure boot, it's just that they're going to be in different areas, because secure boot might prevent some of the regular attacks that you might see. I hope that answered that first question.
Yes, and I actually really appreciate how you said attack the implementation of the secure boot, because that is a very true statement.
Right, yeah. I mean, in theory, secure boot is secure, but it's never that easy.
Right, right.
And then your second question, I think you might have to define trusted boot for me. In my experience, I've seen those used interchangeably, but I might be just missing info.
So looking at secure boot as requiring a cryptographic authentication versus a trusted boot, which is essentially just a value check, integrity check value.
Yeah, well, in the case of a trusted boot, if you just mean like some magic value in Flash somewhere that says I'm okay. Yeah, I mean, in that case, obviously, if the firmware image can be pulled, say, from the vendor website or directly from the device, as we discussed today, you can just kind of look and see what the value is. You can reverse engineer the bootloader, see where it's checking, and then just write to that. So yes, in that trusted boot is a less secure version. So there's other extra things you can look at.
Okay, thank you.
Of course. Let's see. I think we have a question from John or Jean. What kind of testing does a vendor need to do for IoT hardware today? This evolves over time. Yeah, so I think wireless is becoming a lot more of an attack surface for these IoT devices. especially with something that runs on like a microcontroller, it can be hard to fit a good implementation of something like BLE or Wi-Fi inside of 8 kilobytes flash or whatever. So that's an interesting area that I think is new-ish. And I also think one thing that for IoT especially that I see all the time is MQTT. I don't know if everyone's familiar with that or has heard of it. Basically, it's a communication protocol on top of IP that is stateless, sort of publish subscribe architecture for communication. It's huge in IoT. It's everywhere, and it is consistently misconfigured. It is very, very common to see no authentication or no authorization, so that even if they do have authentication implemented, one user with a given username and password can access everybody else's data. It's like the old days of the web again. So it's kind of a new thing. It's immature, and it's a really interesting, in my opinion, area to look if you're looking at IoT devices. Hope that was a good answer.